Welcome back to our controls lectures. Here in our next lecture, we're going to have a great discussion about dynamic models and what it takes to build them. So our first idea is, what is a model? Well, a model is really an informative representation of a system. It could be either physical or conceptual. And by conceptual, we're really thinking about mathematical, something that we can simulate. So mathematical models in terms represent essential aspects such as having the ability to do operations in computation like algebra and differential calculus, but it also must involve a usable form. So it can't be something that's super energy intensive. It has to be something that has an optimized, minimally reduced numbers of steps in order to be able to function and actually be useful for modeling. Thus, in order to build a dynamic model using a conceptual based idea of a model, we would be able to do that using control theory. And in terms, what we get out of that is the ability to help improve our model over time as we keep taking information in and making changes. It can help to aid in training for operators. So a lot of people actually have to perform functions and make changes over time. And those are people who are operators in the field. So it would help us be able to train them and give them something very useful that can actually make big changes in the system that we're operating. It can help to develop effective control strategies so that we can keep making them more advanced and more finely tuned for our specific system, and optimize the operating conditions so that we can reduce costs and improve safety overall. So when we think about modeling, this is actually something you've been using throughout your entire curriculum. So we have first principle models, which are called white box models. They really just help us to build a model from an understanding of different relationships between variables that might exist in our system. As we think about a simple standard box system of we have something coming in, something coming out, being generated and consumed, that is actually something we've been doing throughout mass and energy balances, thermo, and kinetics. There are a lot of pros to this in that we can extrapolate variables and that we don't even need data to be collected, but it can be very expensive, meaning when we're actually modeling this out and we have every possible variable involved, all those variables involve different computational strength, which use a lot more computer power, which can take more time and be intensive to the energy of their system. Also, should be noted that a lot of technology is actually very dangerous for the environment and that it uses a lot of energy to run, but that energy has to come from somewhere, such as petro. Further, we need to be careful in the actual considerations of our models so that we're not neglecting variables and we're not oversimplifying the equation as well. When we think about conservation laws, these are actual types of first principle models that we've been using. So to this point, we've seen mass, component balances, and energy balances. In thermo, you even saw entropy balances. But here, what we're really thinking about is the rate of mass that's being accumulated transiently over time. That's equal to the rate of mass that's always flowing into our system minus the rate of mass that's coming out of our system. And when we think about a specific component of that, as a component mass balance, that's just thinking of the component rate of A being accumulated based on the rate of A coming in as well as leaving, but also the amount of A that's being produced. So the generation and consumption term that we get and really use a lot in our kinetics class. Energy, though, on a different element is based on the rate of energy that's being accumulated by exemplifying the rate of energy that comes in and the rate of energy that comes out due to convection. We can also think about work terms that need to be considered, such as the net rate of heat that's added to the system by the surroundings, as well as the net rate of work that's being performed on or by a system by the surroundings or from the surroundings. And that's actually something that needs to be considered more deeply when we think about the fact that there is shaft work potentially available or other types of work that are actually being performed that may take away from the energy of our system and allow that to not be a perfect system. But these are all based on conservation laws where we have the conservations of mass and energy being applied to our system. And we can use these conservation laws really effectively in building the total energy of a thermodynamic system so that we can learn more deeply about how to simplify these balances so that we can actually use them in exploring control theory principles. We're going to move it back to the blending take example, and we're going to use that example to walk through these balances more effectively so that we can actually see a more deeply derived, simplified model. Using what we just learned, we can now walk back to our blending take example from the previous lecture. In this example here, we have a tank where we're mixing two fluids in input flow rates W1 and W2 with an output flow rate of W. The volume of our tank is V, and the goal of this system is that we reach a transient state that then goes to a steady state assumption. And from the transient state into the steady state, that means that our accumulation term that will exist will ultimately become zero, meaning that eventually the volume of our tank will become constant. But from the very beginning, from the beginning of the operation, we have to consider that there will be a transient setting. So in that, when we consider a mass and energy balance, we're going to take accumulation equals in minus out plus generation minus consumption. And with that, we will be able to neglect the generation and consumption because there is no reaction occurring here. But unlike last time, we will have an accumulation term. We know that mass is equal to density times volume. So when we actually consider the reality of what this term looks like, we will in fact have some type of accumulation term based on our in and out, where the accumulation is truly based on W1 plus W2 minus W. But when we think about accumulation back from even the beginning in 2200, we know that accumulation is based on a derivative function of mass. So it's the change in the mass over the change in time. Because we know that mass is based on density and volume, we can rewrite this as d over dt of rho v is W1 plus W2 minus W. And in that case, we can now actually consider the mass balance through those substitutions as based on this form entirely. So let's consider that outside of our overall mass balance here, that we also want to consider a component mass balance. In considering our component mass balance here, we are going to be thinking about X, where X is once again going to be the mass fraction of A. So in doing that, we have accumulation is equal to in minus out. I'll neglect the generation and consumption terms because this is not a reactive system. And here, we're going to be considering the accumulation term as of our inlets X1 W1 and X2 W2 and our outlet XW. Our accumulation term is once again going to be the change in rate of our mass, but based on our component. So it's going to be based on the accumulation of our mass of A, and that mass of A is specifically going to be based on our rho v, but with X. So mass of X is going to be rho v X. And thus, that is d over dt of rho v X is equal to the above. And that means that we actually have an expression now that we can write out as d over dt of rho v X is X1 W1, X2 W2, XW. So we see that X is in both of these positions. We have W1, W2, and W, which are also based on this equation here, which allows us to generate our overall and component mass balances. We might consider, can we actually now make this a more simplified equation? And the answer is yes. We can consider a couple of practical assumptions that we would think about in chemical engineering. For example, we might actually be able to assume the following. Density, or rho, might be constant. That could help quite a bit in actually expanding this because we can pull out density from both of these terms, allowing us to create this as a variable of just volume, while this one is a variable of volume and X. And in that constant density balance, then we can now apply this rule more in depth. I will pause the lecture so that I can write that out and erase some of this from the board. As we continue working through this, we're now going to be able to take this form and we want to get it in a form that is just dV dt. The reason for that is, if you may notice up here, we do have a term that has a d over dt of v, and by using the product rule, we'll be able to expand that and actually generate a dV dt form. So in order to do this one, we've already pulled out our actual rho term, so we can divide everything by rho, And ultimately, we get dv dt is w1 plus w2 minus w all over rho. And this form is currently complete. We're going to be able to use that in substitution here in just a second. So now let's continue on with our component mass balance. I'm going to go ahead and divide everything by rho. In doing so, I now have d over dt of vx is w1 over rho times x1 plus w2 over rho times x2 minus w over rho x. And with that, I'm now going to be able to use the product rule to expand both of these terms together. And in doing so, I'm going to say v times dx dt plus x dv dt is equal to the following terms as well. Now, we actually have a dv dt term from before. That's from over here. So what I'm going to do is I'm going to move that term over to here so that we can solve just for the dx dt term shown below. In order to do that, I'm going to divide everything by v, and I'm going to try and subtract this side across. And in doing so, I'm now going to get dx dt is equal to, first, our initial terms here that were divided by v, which is w1 over rho v x1 plus w2 over rho v x2 minus w over rho v x minus x over v dv dt, where my dv dt term is w1 over rho plus w2 over rho minus w. And if you notice, we have a couple of like terms that are present and available, and we can group these based on like terms that we wish and rearrange the equation as we desire. For instance, we can base it still off of our flow rates and then divide through. So in order to do that, it will become dx dt is equal to w1. If you pull that out, we have an x1 over rho v1, but we also have an x over rho v. So because of that, we can pull out the rho v from both, and we're left with x1 minus x. We also have our w2 term. So we have w2, which also has a rho v in the denominator for both, which will now be x2 minus x. And we also have rho x vv minus rho x over v. If you notice, we actually have a p that I forgot to write there for just a second. So that is rho x pv and rho x pv all together. The double negative makes that a positive, which means this term actually is gone. Unless we're left with dx dt is rho1 over w1 over rho v times x1 minus x, and rho2 over, my apologies, I keep saying rho, w2 over rho v times x2 minus x. And thus, we've actually now determined two functional forms of the equation. We have a differential equation here for dv dt and for dx dt. Let's consider linearity versus nonlinearity of these systems as we have differential equations. So with these, we notice that this one is a linear form. And what that means is that the only variable condition, like v, is present in the derivative, but not as its own standard form. When we look at this one though, we have dx dt, and while x is a function in both, we also have v. And because of the x and the v that are here together, we actually have a cross entanglement, meaning this is non-linear. So in that form, and what that means is because this is sin x, and x and v are both changing, that while this one is linear and this one's non-linear, the total system is non-linear. If one of them is non-linear, they are both non-linear. And thus, while both of these equations can help to model our system, we're going to use them in tandem in order to approach so. At this point, this is where the class becomes fun for simulation, and that we can actually now see what's happening over time in a dynamic form as these are changing. Ultimately, they will eventually reach zero. There will be no more change in the volume, there will be no more change in the component, and thus will be at steady state. But Any type of deviation from that means that our controller wants to keep us at steady state and has to make appropriate changes in order to reach dx dt to be 0 again and dv dt to be 0. And thus, in order to do that, we have to understand how these systems work and able to model them so that we can create a proper control environment. As we continue our discussion, we're going to be looking at black box models. Now, these are very data-driven models in that we have a desired function that we want to approach. We have a process here which has an input of u leading to an output of y. And we want to see how we can actually model y based on our input values. If we want to model y, we need to have a lot of data. But we also need to use a function that could be fit using that. So our function is going to be based constantly on new information, where we're going to take in the input value over time and also the last output that was measured or previously used. And that is going to be y of t minus 1. Ultimately, we can generate a function for this of y of t as a function of both, where this function could be of many different models. This could be a polynomial, it could be a neural network. There's a lot of opportunities available for us to be using. There's a lot of pros to be using this as well, in that it's very universal in its applications, meaning you can use it to evaluate a lot of different functions. It's really easy and fast to use, and we have a lot of them standard available for fitting modeling equations. But unfortunately, there are some cons in that a lot of this is under the hood, meaning you have no information about the system at all. It is just a process. You have no valuable information. You're just taking into consideration the input that you had and constant new information of what's coming out, meaning it requires a lot of data to actually train this model and to get it to be valuable. Thus, there is an opportunity to combine both of the things we've just discussed, our white box and black box models, and call a gray model. So our gray box model is a semi-empirical method. It uses both of these equations that we've designed from our courses, as well as fitting and modeling equations that we've seen here. Let's consider a transient CSTR, which is a continuously stirred tank reactor. For our transient CSTR, we're going to assume that we have constant volume and temperature of our system, meaning we have exactly the same amount with flow rates coming in and out, and they're going to end up being the same. There's no accumulation term, and what we're talking about to be transient here then is actually the amount of A that's present and the amount of B that's present. At time equals 0, you have an initial amount of A that might be present, and it might actually be none. But you always have a certain amount of A coming in, and you have a varying amount of A that's leaving because of the reaction occurring in the system. We're going to assume that the densities are constant of A and B, that there's perfect mixing in the system, and we're going to take a semi-empirical approach to determine the first order rate reaction. And so our semi-empirical is going to actually say that we can model the reaction rate based as negative K times the concentration of A, or Ca. And that's based on A going to B in a first order model. And now, taking this from kinetics, we're going to be approaching this from our white box using mass and energy balances, and now our black box as just a standard fitting equation of what is going to be the reaction rate. So I've taken into consideration already our overall mass balance. We had an accumulation term and a generation and consumption that all went to 0, and we found that the mass in equals the mass going out. And thus we can consider that as our rho v dot, where in this case, our rho that's shown right here is actually, funny enough, going to be a volume flow rate. It can be a little confusing, but that's okay. My rho's and v's look very similar, so I even confuse them. Totally meant to say that in this reality, our Q is going to be our flow rate there. So as our volume flow rate is going to be the same, it matches that our volume flow rate maintains the same as Q. Thus, we can consider that because mass of A can be seen as specifically the concentration of A times the volume, that we can build out a component mass balance as well from our white box models. Our component mass balance actually is going to be modeling a transient system, which includes the reaction. Now I've grouped a reaction term that combines the generation and consumption terms together so that we can see it really as just accumulation with the ins, the outs, and our reaction. Ultimately then, we can take this form as d of dt for our mass of A is equal to our mass flow rate in, our mass flow rate out, and a reaction of A with the volume of the system. Now we know what the reaction of A is. It's minus kCa. we know the volume is constant, and we can model our mass flow rates in using our concentration term. Because taking m equals CV, we also know that m dot is CV dot. Because we know that V dot is now Q, then we can actually use this approach to say CA times Q. And we can take that information into account as we model out the system and apply this directly. Our MA here is going to end up being the CA of V, therefore d of dt is going to be our CAV, and that's equal to our mass flow rate in, which was QI CAI. Our mass flow rate out is going to be QCA. Our reaction is going to be minus KCAV. We know the volume is constant, so we can pull that out of the full expression entirely. Dividing V on all parts, we see the division there becomes dCA dt, which is equal to now QI CAI over V, QCA over V, and KCA. Notice that we have a couple of those V terms, but we also have a couple of those Q terms. Now, we know that QI is equal to Q, so we can actually go ahead and just call this Q. And we can pull out directly now Q over V for our CAI minus CA, and we know that we can also subtract KCA. So in this form, we've been able to denote a linear equation where dCA of dt is based off of our constant value of Q, our constant value of V, and CAI, CA, and K. Now, CA itself is changing, but CAI is going to be based on what's coming in. And unless CAI ends up being a disturbance variable that starts to be changing, then this really starts to really model off of just CA over time. In reality, our flow rate can also vary, and this will change really the amplitude of the equation that we're able to model here with this. But ultimately what we've done is we've combined an empirical and non-empirical approach to create this semi-empirical gray box approach to really studying this more fundamentally. And we're able to see over time and model out through simulation how the concentration of A changes as we go from this transient system into a steady state approach. And ultimately, we would hope to see that we would reach a constant value, and that would end up being what we can model through control theory. Let's continue forward with the degree of freedom analysis. So degree of freedom analysis is something that's talked about initially in 2200, but we're going to walk back through it today. A degree of freedom analysis allows you to figure out exactly which variables exist in your system, which constants are known, and what equations can be used to help to solve through your systems. In doing so, we want to be sure to reach an exactly simplified solution at which the number of degrees of freedom become equal exactly to the number of variables that are known minus the number of equations that could be used. An undersimplified number of degrees of freedom means that we can't actually reach a solution, but an oversimplified means that things might interfere and conflict. So we want to always reach an exactly simplified solution. So how do we do that? Well, there are 5 steps if you want to consider. The first one is to list off all of the constants that we know in our system. What things can we assume to be constant and are not variable? Next, we'll look at the number of equations that are possible based on modeling and simulation, and determine the number of variables that are left over. Time doesn't count. It is not a process variable. It's just always happening. Next, we can think about the solution of NF equals NV minus NE, our standard equation. We can associate in step 4 the output variable with NE and from which equations and models that might exist. And finally, we could determine which NF input variables are based on our MVs and our DVs, which of course are based on our variables that we can manipulate or that we cannot, which are disturbance variables. So let's go back to our handy blending tank example here. We have a blending tank above me, and shown here is an input of X1 and W1, another input of X2 and W2, as well as an output of X and W. We've already had discussions about V and rho, where we've seen that over time the volume might change and the concentration might change for our component A, which we're calling X. In doing so and really looking through this, what we find ultimately is that we've been able to model these equations already in a previous study. And in doing this, let's break down each of the steps as we approach solving this problem using it. So in step 1, we're going to be looking at the parameters that are used to determine this system. So the parameters may simply be what are involved in this system. And the parameters that we're looking at exactly are actually time, as time is what we're always a function of, as well as something that we know is going to be constant, rho, our density. Next, we can be looking at variables. And those variables that might still exist here in our solution. So of that, we are going to be considering in steps 1 and 2 together this back and forth of which things are constant, which things are changing but we can't control, and which things are variable in the equations. Of that, we have a couple of variables to consider. We know that v is a variable, it is changing. We know that x is a changing variable. We see both x1 and x2 are present in here. We know that w1 and w2 are also in here. And we also have w. So total variables that exist in our current system, 7. What kind of equations do we have available? Well, some equations that we have and we've used in the last example to get to here were our overall mass balance and our component mass balance on component A. Thus, we have 2 equations total. In solving this equation, NF equals NV minus NE, that is equal to 7 minus 2, which is 5. Meaning we still have quite a few things that we cannot necessarily solve for. Of that, let's look at step 4. What are the output variables that are existing here? Well, the outputs that we're really thinking about are actually based on V and X. We know that we're going to be modeling based off of V and X, and those are the actual things that we're really considering that's happening here when looking at these two together. Thus, the equations that we're really based off of here, the 2 equations that we have, allow us to model, because that's what we're looking for, are the equations and models for V and for X. Finally, in step 5, we're going to be determining which of these, based on our degrees of freedom, are input variables that are manipulatable or are disturbances. What can we manipulate and what can we not? So breaking that down, we know that we had x1, x2, w1, w2, and w. We know that's left because when we look at all 7 of these variables, we've already now taken out 2 of these. We've taken out v and x. And in doing so, we moved them into step 4, which is specifically our output variables. And we knew that was the case. So what's remaining are input variables. We have an input variable of x1 coming in, so we know it has to be there, as well as for x2. Other inputs and variables of those that are associated are going to be w1 and w2. And ultimately, we have an input variable to our modeling system, which is w, ultimately. Those are all going to be inputs to our ultimate equations when we think about them here as our modeled equation systems. Based on our initial discussion, we know that x2 is equal to 1. It's just pure component A. So at least for that one, we know that we have something already present. It may not be an equation that we can use directly, but we do know that it is true. And in looking at these more deeply, which of these are things that we can manipulate and which of them are not? Well, we know that we can manipulate W2, as we discussed that we have the ability to actually tune and tweak it, meaning this one is an MV. W1 we have no control over though, therefore it's a disturbance variable. X1 at the same time is coming in and might manipulate and change out, and thus we have no control over that one. And ultimately W, what's coming out as our ultimate flow, that is actually something we can manipulate. Therefore, that's going to be another MV. And thus, we've been able to perform a degree of freedom analysis on our standard blending tank situation, and we're able to use this kind of idea in order to blend together these lectures 1 and 2 as we discuss these more in depth.